because of the maintenance and the labor to install it. People are going more to the inline, and the inline can handle many more different applications within our landscape. So as what we have is we have two layouts. Okay, when you're designing a system, where you're going to be thinking about two different layouts. One is what we call a light system, where we're going to have a valve, filter, and a pressure regulator up front connected to the main line. And then we're going to connect the NetFM tubing, or the inline tubing, and we're going to snake it out through the shrub bed. And then we're going to bring it back in on itself. Okay, very quick and easy install. These tend to be used in residential applications, smaller shrub bed applications, and flower beds. Okay. And we'll go through the parts and the pieces later of how they get connected and what we're doing. The grid system, which is this one over here, will have a valve, filter, and pressure regulator. And then we have what we call a supply header. And that supply header is that piece of PVC going out there. And then we connect into that supply header with our tubing. And then the tubing goes down through the shrub bed, and then we have what we call an exhaust header, which is this piece right here, okay? Then on that we put a flush valve on this side. This header here is not connected to this header by any other means other than the inline tubing, okay? So as what happens is the valve turns on, the water flows through that header, flows down through the inline tubing, and then the whole system's charged, and as what happens is the water's actually moving in a couple of different directions within the tubing. And then the emitters are irrigating and applying the water, and going from there. This valve down here, this is mainly a manual ball valve, and as what it does is it allows us to open up the system and drain it in the fall for winterization, and or it allows us to flush any dirt and debris that maybe got in the system from, someone cutting the tubing or something like that on a repair. They'll open that ball valve up while the system's running and flush the dirt and debris out of the system. Okay. So the trick here is first of all, am I going to be designing a light system, or am I going to be designing a grid system? That's the first thing as a designer that you're going to be thinking about. After that, then you need to determine what emitter flow rate I'm going to be using. Is it the 0.26 gallon per hour, or the 0.9, or the 0.6, or the 0.4? And then a what emitter spacing, and then how far apart am I going to put my tubing? When you're designing that drip, that's primarily what it is that you're looking at. And we'll go through that here in a second. Okay? So, this is a slide that I use for my contractors, so I say you should already know how to use drip in a planting bed. That might not necessarily be the case in this application, but the major difference between drip irrigation and overhead irrigation is we're not so concerned about what we're irrigating, whether we're irrigating turf or flowers or those kinds of things. We're more concerned about the soil in which we're applying the water to. As we have a higher clay soil, we know that we have to apply the water slower to that clay soil, or else it starts to run off. And so we're much more concerned about our soil types than we are. The type of plant material that we put in our designs or our planting beds that we're irrigating is what that's going to dictate is how long and how much water we're going to apply on a daily or weekly basis, okay? And it's the soil that the water is moving through that we're trying to keep the roots alive for the plant material. So that's one of our biggest concerns that we're looking at. Okay. Okay, so here comes our soils class, and I apologize for doing this. The first class of the morning of the week after a 3-day weekend, I apologize. It's not fair, I know. But basically, is what this is showing is an irrigation manufacturer took a look at the different soil types that we have, and is what they did is they looked at the rate in which the water moves through those different soil types. So when we look at a clay soil, the water moves very slowly through there. When we have a sandy soil, the water moves through that sand very fast and tends to be more vertical, where the clay tends to be more, the water tends to move more horizontally in the soil profile. So what they did is they looked at the United States Department of Agriculture, this chart, and basically is what they did is the rate in which that water moves through the soil, they converted it to an emitter flow rate. So when you choose, and you'll see this here in a minute, but the emitter flow rate, remember when I showed you 0.26, 0.4, 0.6, 0.9, basically is what that's saying is okay, if I have a clay soil, I'm going to use a certain type of emitter flow rate. If I have a sandy soil, I'm going to use a different emitter flow rate. So that's why we did this. So those emitter flow rates match up exactly with the rate in which the water moves through the soil. And as what they found is by matching up the emitter flow rate with that soil type, that they can move the water farther and faster in that soil than applying a higher flow rate emitter to that soil that might not be able to handle that flow rate, if that makes sense.
A question.
Yeah.
I'm assuming the cover in bare is there's plants that are shadowy.
Correct. And primarily because the big thing here on the bare and the cover is that if we have a bare soil, no cover over the soil, that soil tends to dry out. And we know that it's much harder to move water through dry soil than wet soil. So we have a lower application rate in bare soil because it tends to be drier. Once soil gets moist, typically on the drip side, we want to keep it moist. We don't want to let it dry out, because once it's moist, we can move the water in our soil profile much easier than once it dries out. It takes a lot more water to do that. So that's one of the tricks. Okay, we've all seen the soil triangle. I'm not going to go into that. Okay, but soil pore space, the space that's between the particles, we're basically having soil and water in there. When we're looking at a sandy soil, the range of surface area is 35 to 50%. That's how much space there is in the sandy soils. When we go to a medium, fine textured soils, it's 40 to 60. And then when we get into a clay soil, it's somewhere between 55 and 75%. That just means that there's more surface area in our clay soils because the particles are a lot smaller. Okay? The process of the water, the interface is what we were talking about on that chart. The rate in which the water moves through the sandy soils, the larger those spaces are, the easier for that water to move through those soil particles. Okay? The other thing that we need to look at is the soil particles are negatively charged and then the water is positively charged. And so once we have that attraction, once the amount of water gets in there, it reduces. The stronger that bond is, the drier our soils, the stronger that bond is, the harder it is to move that water through the soil. Once we add more water to it, the greater distance that we get in there, the less tension we have in our soils. And I apologize for even going into that, but it is what it is. Okay? I would hate going through that, and that's why I went over it very quickly. So here's our design steps, okay? So if you have your catalog, and you can follow along in the catalog, and you can kind of follow along in that handout, page 8 in the catalog, okay? And you'll kind of see what it is. This page 8 really is kind of what we're looking at from a design application. These are the steps that you're going to go through. So we're going to be basically looking at the general guidelines chart there. And the first question it says in that chart, are we irrigating turf or are we irrigating shrubs and ground covers? Can you guys see that? Okay. So once we answer that question there, then we're going to look down and say, what's our soil type? Okay? Do we have clay, loam, or sand? And that's basically what this chart right here is showing. If we have a clay soil, we're going with a 0.26 GPH emitter. If we have a loamy soil, a 0.4, and a sandy soil, a 0.6. So kind of ties back into that soils that we just talked about, that we're applying the water slower to our clay soils so that we don't get that runoff, and faster in our sandy soils, okay? So I will tell you right now, 85% of the soils that we deal with in the United States are clay. Because we're a glaciated continent, we have a lot of silts and clays in our soils, and that's the challenge that we have. We do have some sandy areas, but not very many. A few loamy areas, but primarily clay is what we're dealing with. Okay? So the answer number one is we're going to go with a 0.26 in our clay soils, or whatever emitter flow rate. Okay? Now is what we need to determine is how far apart we're going to have an emitter in our tubing. There were three choices. There was a 12-inch spacing, an 18-inch spacing, and a 24-inch spacing. Okay? So when we have our clay soil, when we look down there, emitter spacing, it shows us what we're looking at. Clay, we're putting our emitters farther apart. In our sandy soils, we're bringing everything closer together. Okay? Now is what we need to look at is how far apart we're putting our tubing together. Remember that grid, when we were looking at that grid layout at the beginning, we had that exhaust header that we were connecting to. Now we're just determining how far apart we're putting that tubing in that connection. And again, in our clay soils, everything's 18 inches apart, and in our sandy soils, things tend to get closer. And it does make a difference whether we're looking at shrubs or grass. Okay, a lot of math here. This is not a math class, and so I'm not gonna make you go through and calculate all this fun stuff, because who has smartphones? If you have a smartphone, there's an app out there that you can buy it and it'll do all the calculations for you. So, hint for your test, if you ever have a test on it, just get the app and you're good. Do they let you take your phones in your tests? No? We could. We didn't have smartphones. We had the old HP calculators that we'd program all of the calculations in, and then we just enter in the numbers. That's how we got around it. So the other thing that we need to figure out is how much tubing, and we'll actually go through this here in a few minutes. But there's a calculation on there, and it's on page number, on the calculations of how much tubing that we use. It's probably going to be in the very back. Page number 63 is where you'll go through all your calculations on your tubing. We'll come through some real life. We'll put the board up after this, and we'll actually go through this and figure this out so that you guys can see how this works. But basically, is what we're trying to do is we're trying to figure out how much tubing that we're going to be putting in an area, because that's going to tell us how many emitters that we're going to have and what our flow rate is, and we'll go through that and figure out what our flow rate is so that we can size our valves and our filters. Okay? So now we have that header. Remember those headers that we had? The supply header and the exhaust header? One of the questions that we need to figure out is how far apart can we do that? If we have a median out in a street and it's 1/4 mile long, it's 1,260 feet, can we have our headers, can we do that in one zone? Okay, what kind of distance are we looking at? So is what we're wanting to do is we're going to have our different pressures are going to allow us to go greater distances. And so we're going to look at what size of pressure regulators we're going to specify in our design. Are we going to go with a 15-pound pressure regulator, a 25, 35, or 45-pound? Typically with the inline drip, you're always going to want to go with the higher flow or the higher PSI pressure regulators, because it's going to allow us to go a greater distance. And that's shown here on this right here, that if we're using a .26 with a 45-pound pressure regulator, we can go 877 feet between our headers. If we specify a 25-pound pressure regulator, we can go 604. Okay, so those are some of the things that you're going to look at when we're designing this. Okay, so that's a question or an answer that we need to have on there, and we'll look at that. Then the next thing that we need to look at is how much water are we putting in there with our tubing. And basically on this chart right here, on the flow per 100 feet, you can look at your emitter flow rate that you're specifying, and then you can look at the spacing, and it will tell you for every 100 feet of tubing your flow rate is 0.67 gallons per minute. And then if you have 1,000 feet of tubing on there, then you can do the math really quickly on what your flow rate is for that area or that you're looking at. Okay? We'll come back and make this real world after this. I'm just kind of wanting to show you what the parts and the pieces are here really quick. Okay? So one of the challenges that we have with drip irrigation is because we can cover such a large area with a small amount of water,